Okay, great.
Hello everybody, I'm Srijit Chandrasekharan and this is my presentation on my survey on adapting LVCSR to intrinsic variations of speech. So this is the outline of the presentation. We'll talk about the objective of this particular survey and then the introduction to LVCSR systems, which are large vocabulary continuous speech recognition systems, which are most commonly used technique for most of the speech recognition systems in real life. Then the acoustic aspect of the human speech, which actually results in different invariance techniques for the speech. Then the conventional adaptation techniques and the drawbacks of those. And then the drawbacks resulted in this state-of-art techniques, and there were a few improvements which was seen due to that, and the future scope of the research for that. So first is the introduction to the LVCSR systems. These LVCSR systems are systems in which the context depends on the context. They have a sort of invariance for that. And then there is large vocabulary which is of the range of 10 raised to 3 or more than that, that is 1K or more than that is the vocabulary size of those. And then we have the quality that it is tend to suit for the natural speech, which is something like in a meeting room when people speak, they will speak continuously. So those sort of speeches are dealt here in large vocabulary continuous speech recognition systems, and its application include dictation, audio indexation, and spoken language dialogue systems. In real life, you can see some speech recognition systems such as Siri, or in Microsoft, that Windows sort of softwares, you can see a few speech recognition systems which work on this basis, which tend to convert the large the continuous speech to text, or maybe to recognize the index or something like that. Now we are coming to the acoustic aspect of the human speech. So in the acoustic aspect, first we can explain about the source filter model, which is the human speech model. So here is a source, which is the vocal fold vibrations. So in our body we have the vocal folds, which actually create a pressure fluctuation. Using the air or breath that is coming from the lungs, it will create pressure fluctuations, and these act as the voice source for that. And then there is the filter, which is vocal tract and glottis. So the glottis is responsible for the voice signals, and the acoustic aspect are based on this kind of a model. So there are physiological and behavioral factors which include the age. For children, there will be the vocal tract which are small. So they tend to have a shift in the fundamental frequencies or the formants, and there are pathologies like breath problems, or some people can have diseases which affect the normal breathing. So there is a kind of variance from the normal adult speech in all these cases, and the long-term habits such as smoking or something like that. Then the other two aspects are these: long-term modulations and co-articulation and suppression. So the long-term modulation comes into picture when the speaker's mood changes. So in a pressure kind of situation or something, the speaker's mood changes, and it tend to affect the normal adult speech. And intentional modifications can be there. If somebody wants to stress something, emphasize something, then that will affect the normal pronunciation of a word. Other important things are included here, which are accent variations, which can be there for the native speakers also. You can think about an example where a British speak English and the US citizens speak English. Those are acceptable kind of accents, but they tend to be different. So there can be different kind of pronunciation for same word, which we need to deal with. And the foreign accents are there. Foreign accents is when somebody from a different foreign country want to speak a particular language, they tend to replace the phonetics of one particular language with the phonetics which they know. So that will affect the speech recognition systems considerably. And the foreign names, it's the most difficult part of the LVCSR systems. They cannot really adapt for the foreign names, which will be totally different for the foreign language. Then the spontaneous speech. in which case a person speak fast, he will tend to have slurred pronunciations. So that will also affect LVCSR systems. So we are now into the conventional user adaptation techniques. So there are two different set of adaptation techniques when we consider the conventional techniques. First one is the front-end adaptation technique, and there is another kind of techniques which is called the acoustic modeling techniques. So this front-end is the place where in an LVCSR systems we generate the actual features. So the features can be generated in two ways, mainly two ways. There are other important, other non-important methods also, but these are the two important methods which are used commonly. So this vocal tract length normalization is one technique in which we use either a frequency warping, which is linear, or Bart-Mill wrapping, which is warping, which is non-linear. But it has a disadvantage that it is a time-consuming technique, because to find this warping factor, we need to have a lot of computations. So it will have the disadvantage that it will always be time-consuming. The second front-end adaptation technique, which is much more used commonly, is FMLLR, which is the feature space maximal likelihood linear regression technique. They use affine transforms to transform into the features, and they also use the maximal likelihood criteria to find out the proper features. So now we are into the acoustic model adaptation techniques. So there are two important techniques which I will be explaining here. One is the maximal likelihood linear regression. So here we use the transformation matrix for HMM. HMM I didn't explain, I will explain now. It's actually hidden Markov model, which is used for speech kind of signals, where we will observe some variables, but it will not be the thing. There will be other latent variables which are unobservable. So those sort of variables are also dealt with HMMs. So in maximal likelihood linear regression, we use expectation maximization algorithms. If you have done the pattern recognition courses, you might be knowing this algorithm. In the first step, it's expectation, where we actually take the observable variables and convert it into posterior probabilities, which is maximized in the next step, the maximization process. So it will maximize the hidden variables probability also. The disadvantage here is that there can be an unreliable estimate if the training data is insufficient. So to rectify that, we have maximum a posteriori method, which actually results in a posterior probability, which can be used here also. So the next technique, which is the agent voice based adaptation. So here we have the all kind of distributions, and from those distributions we generate some mean vectors, and the concatenation of those result in super vectors on which PCA is used. So this has the advantage that the final model will not be having too many parameters. So it tend to have faster adaptation also. These are a few drawbacks of the conventional techniques. Actually, the conventional techniques are meant for the normal adult speech, but it will not be able to deal with all different speaker invariance kind of problems. So the problems where small adaptation data it cannot adapt, and there was the problem that when large-scale speech tasks are there, it was not able to adapt, and it was not able to provide a robust method for in the presence of noise. So there was another effect also, Lombard effect, which is called, which happens when a person speaks in a noisy environment, and the person tend to speak in louder voice. That's the normal tendency of any speaker. So when they do that, actually the fundamental frequencies can shift a bit, and it can increase the duration of vowels, and so many effects can happen. So this Lombard effect was not dealt in the previously explained the conventional techniques. Then based on the age we are not able to adapt. Then the spontaneous speech, for that also we are not able to adapt. And the word error rates, which are a measurement of the speech recognition systems, was always high. So we move to the state of our techniques, which is non-linear. The previous methods were all linear. Now we are moving into the non-linear space. So one of the important non-linear method is the kernel method, which is actually based on the linear method, but those use the non-linear techniques here. So in the place of PCA, we are using kernel PCA here, and the supervector space, which is non-linear, is converted into linear space, which is in multi-dimension with the kernel tricks. So there are two important methods, which is EKVE and KEMLLR. These are the two important techniques which was used in the kernel methods, and these both were based on the previous method like agent voice method and MLLR, but they were tend to be non-linear because we are using a kernel here. The advantage was the fast speaker adaptation and noise robustness. The second important aspect is the aspect model reference speaker weighting. So there is a particular technique of speech which is called reference speaker weighting, in which we will have weights for each of the speakers. Each of the speaker model we will have a set of weights which actually adapt them to the particular model. So these speaker models are overlapped, and we can create a model which is speaker invariant. So this linear combination of reference speaker weighting was used with agent voice method. This was the technique which is called aspect model based technique, and here the main advantage is that we don't have to use too many parameters. So that will always help in fast adaptation, because we don't need to populate many parameters for recognizing the speech, and the requirement of adaptation data was considerably small. So we require a few seconds of adaptation data to switch to a particular type of speaker. This is the final method or final set of methods, which is called the neural network techniques, and there are two kinds of neural networks. So the neural networks, these are context dependent neural networks, and they have the advantage that they are not using the GMM-HMM, which is the Gaussian model based technique. So it's actually moving out of the normal kind of Gaussian techniques, and then they have the ability to extract the discriminative internal representation. That's the features that they extract are not dependent on any kind of speakers. They tend to filter out all the internal speaker dependent representations. So these are insensitive to the sources of variability, which are like maybe age or something like that. And we use this particular technique, feature space discriminative linear regression, which tend to maximize the entropy of the features. So in the previous technique I explained, which is called MLLR, they tend to maximize the likelihood. Here the entropy is in picture. The second important technique is in neural network is the deep convolution neural network. Here we model the input correlations and the translation invariance with the fewer parameters. So we will use these three techniques, which are local filtering, max pooling, and weight sharing. I'll explain each of these. The local filtering technique is something where we use filter parameters which are for local parts of the input speech. So they tend to have a spread over the total input space. And the second one is max pooling. So these neural networks, as you may already be knowing, have different layers. So these layers are made of activation functions, and each of the layers will have a specific property. So there are two layers in this particular network. One is the convolution layer, and the second is the max pooling layer. This max pooling layer is responsible for the translation invariance property of this particular technique. And the final thing is the weight sharing. In weight sharing, we have the weights for each of the filters, and these filter weights are actually convoluted with the input speech to generate the parameters for acoustics, which is used for the speech recognition. So the improvements with the modern technique. Here we require small adaptation data, and large-scale speech recognition was made possible, which was not the case with the conventional technique. Now the fast adaptation is more possible here, and it is robust against noise more, and the environmental parameters also. In addition to the speaker invariant property of that, it's also robust against the noise which is present in the environment, and it's also able to adapt to the spontaneous speech. Finally, the multi-speaker environment, which is something like in a meeting room when multiple speakers speak, they tend to overlap the signal. So those kind of problems will also be dealt with neural network technique, which is also made possible. And the WER, which is the word error rate, became much lower, something around 10 to 20% for this particular set of evaluation for the speech. So these were the advantages by using the new techniques, but those were non-linear, so a bit more complex. And now we are coming to the final slide, the future scope. The future scope can be something for the adaptation of speech impaired people, something like dysarthric speakers. These are the current research going on topics, and reducing the WER to a negligible rate, something below 5% or so, so that it can be used for any kind of real life applications, and it will be more reliable. Then there can be some kind of a technique which can use the speaker and environment parameters to adapt to that sort of a setting. Here we can also make use of the speaker's individual information if it is available. In that way also it can improve it a bit.